Good morning, everybody. All right, so what we are going to cover today is a new data structure called Binomial Heaps, which takes some of this idea of trees and so the heapification properties. And what we're trying to do is try to address a specific issue, which is what happens if we need to merge multiple priority queues into one priority queue. So here I have the pages for the notes and how we're going to use these binomial heaps in order to be able to create another type of priority queue. And then what we're going to do at the end of lecture is we are going to compare the different priority queues that we've created over the course of the semester. So the first one we built with a sorted sorted doubly linked list. Then we built one with a minimum heap and a maximum heap. And then we're going to build one with a binomial queue. All right, so the first thing I want to quickly mention before I get on with the lecture, well, a couple things I want to mention. So the first thing is you make sure that you coordinate your weekly code review with your project manager, and you need to complete these every Monday through the rest of the semester. And I have provided the script that I've given to the project managers. So if you go on the link, you go on the lecture schedule, you scroll down to this week, you'll see here that I have code review script. So if you click on this, it will download a PDF for you. And what this is going to do is this is going to tell you what the TA is going to be doing while they're going through your code. So the questions they're going to ask, the expectations, how they're going to be grading it, and so on. Another benefit to you is that in the event that you might want to do project management in the future, this is an opportunity for you to see how to kind of manage. And I've given them a lot of advice on how to handle certain situations. For example, when giving feedback, if they're writing something up, they should make the critiques about the code, say the code may be strengthened or the proposal may be strengthened with, and describe that, whereas compliments should be about the people. So that way you're providing opportunities for them to be able to correct the product, but when they're clearly doing good work, it's positive reinforcement. So this is all there, and I've provided it so that way you know precisely what it is that they're going to be doing and what where they're coming from when they do this. The second thing I want to point out is that I have now made your current average in the course available on Sakai. So if you go to the grade book, you'll see at the very top that your current average is there. The reason why I didn't release it until now is because up until this point, there's a lot of fluctuation. We just started the pre-ternship, so small deductions would have a disproportionate effect on what your final average should be. But now we're kind of at the point where you have a full proposal, you have the resubmission, you have the first memorandum, you have the questions, you've developed a pretty solid number of points. So therefore, it's going to be a much better reflection of what your final grade is going to be going into the final exam. So that way you don't panic if there's small points that are taken off. And so because of that, the report that I sent out a couple weeks ago or last week, you're going to notice that your grade in the system it's highly likely that your grade in the system is higher or significantly higher by several percentage points than what I sent out to you, and that's why. Okay, so the other thing, for those of you who are here, you may have noticed that the Pup Professor has graced us with her presence. This is my dog, Erin. I brought her in kind of as an opportunity to help everybody kind of just get a mental break. So if she's walking around and you're inclined to pet a dog, please feel free to do so. You can call her over, I won't mind. I call her the Pup Professor. She's a golden retriever Irish setter mix, so it's almost like she's destined to be here on campus. And I also took this picture because I brought her into the Introduction to Computing class last week, and they're all working on a coding assignment. So she's up at the front, and it looks like she's giving the lecture to the entire class. So I found that quite amusing. I thought I'd share that with y'all. Okay, so up to this point, we have designed these two priority queues that I reviewed with you. And we had advantages and disadvantages of each. So with a sorted doubly linked list priority queue, the disadvantage is that insertion took on average big O of n time. And if we had to insert n elements, then the overall time becomes big O of n squared. The advantage, though, is that because we have the head pointer and we could do pop front in a queue, this means that we can do deletions in big O of 1 time. Then we went with a min heap, and the min heap, we have big O of log n insertion, and then we have big O of log n deletion. And the reason why we had to say big O of log n deletion is because even though the element is at the top of the heap, the way it worked is because it has an underlying dynamic array, it moves the element at the end of the array up, and we have to heapify the elements down. So it has a drawback of log n deletion. So in priority queues, we've used priority queues in several places. We've used them in Dijkstra's algorithm, finding minimum spanning trees. We've used many of you found really cool applications in Creativity Challenge 3 to apply the priority queue that you built from the doubly linked list. And when you get into the algorithms course, there are going to be several instances when you need to perform an operation called meld. So I have a ulterior motive in introducing binomial queues. Binomial queues are the precursor of a data structure you'll learn in algorithms called a Fibonacci. And the main idea is you want to be able to combine these priority queues in order to be able to perform several tasks. So the issue is we want to be able to meld them. And we've already kind of done that with a doubly linked list. Remember we did that problem where you have k-sorted doubly linked lists, and we went through and figured out how to put them in. So what we did is we took them off the front, but we actually used a min heap to do it, right? So standard binary heaps, though, aren't exactly great for combining, because they're actually 2 dynamic arrays and they're not guaranteed to be in order. So let me give you an example. So let's say we're trying to meld these 2 max heaps. And so what's going to happen is we're going to check the top and then pop the larger one off. So then we would have 22, and we see that 14 is now at the top. But in order to do that, we have to take 7 and move it down. Then we do the same thing with 18. And we have to keep doing this at every single stage in order to get all these elements and merge them and melt them together. But now what I like to do is I'd like to kind of take the way that we've approached several computational and critical thinking approaches and put a little twist on it. So we're going to go all the way back to binary addition. So in binary addition, what we would normally do here is we would say we have sum, carry bit, and carry out. So this would be 1, so 1, 1, 0, carry bit becomes 1, this becomes 1 with carry of 1, and so on. And we get this result, right? But let's think about this in a different way. Let's think about this in clusters. So this is the same problem, but I'm clustering them in powers of 2. So power 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, and so on. Here, the way this problem works is that we get the solution of 37, and the reason we get the solution of 37 is because we have an initial 1 that we add, and then we added 4, like so. Then we had 4. This becomes 8. This is 16, and then 32, right? So we have 32, then we have 4, and then 1. So the way we could combine this even further is we could say 1, 2, 2, and then we would say, well, that's 4, right? Then we could say 8, Well, 8 plus 12 is not a power of, excuse me, 8 plus 4 is not a power of 2, so that's just 12. But when we put 16 here, what's going to happen is that we're going to see that this becomes 32, 4, and 1. So that gives us our solution. So these binomial heaps are going to be working in a very similar way. How can we actually combine powers of 2 to be able to manipulate how we understand that something is the top element in a min heap? I'm sorry, in a binomial queue. So let's take, for example, these set of numbers. So here we have kind of a block. We have 26 and 31, and those are in their own blocks. Then we have 53 and 58, and then we have 2 blocks of 4. And in the first block, we have 23 is the smallest, and in the second block, 23 is also the smallest again. So what we see here is if we're adding these together, we could say that this is 4 and this is 8. Does everybody see that? So this is a potential way of being able to figure out how to structure this data in such a way that we can come up with a potential solution here. And so what happens is if we want to find this, let me stop here for a second. If we wanted to find the smallest element, all we'd have to do is know the smallest element within each block. And so here the smallest element in the first block is 26. The smallest element in the right block, the left block that has 8 elements is 23. So all we have to do is 23 is less than 26, and we are able to get our smallest element. So kind of getting back to combining this idea of addition with this idea of building a heap in order to be able to perform an operations. So if we're clustering them in powers of 2, this is where we get these binomial ideas. So the packets must be in powers of 2 and must be able to efficiently fuse packets of the same size. I'm going to show you animations, how we do this in a moment. So basically what would happen is if I have 2 packets of size 4, I should be able to fuse them into a packet of size 8 while simultaneously still being able to figure out in big O1 of time what that smallest element is. And then here's the crucial part. If we can efficiently meld 2 priority queues, we can efficiently enqueue elements into the queue. And so here we have another set of elements, and now we have an issue. We have 8, we have 12, 13, 14, 15. Now, in the end, what we would want to do is we would want to, let's say I want to insert 17, right? So 17, if I put 17 in here, what we're going to see is we're actually going to combine these into from 1 and 1 into 2, 2 and 2 into 4, 4 and 4 into 8, and 8 and 8 into 16. There we go. All right, so our analogy with arithmetic breaks down when we try to remove the minimum element. So what we're going to try to do here is we are going to try to figure out how to break the blocks down. So for example, in this particular case, 26 is the smallest element. Now what would happen is, okay, sorry about that. So let's say this was 17, so the animation wasn't quite right. So if I had 17 here, what would I want to do is I would want to pop that value off, and we would see that this would give us this remaining block. So we have a block that no longer holds a power of 2. But when we remove 1, we see what's going to happen is we have 1 plus 2 plus 4 left. Does everybody see that? So when I had 17 here before and what the animation should have been, then what's going to happen is that had 8. And so what's going to happen is when I remove an element from any of these blocks, this is going to be some sort of 2 to the n minus 1. So when I have this, if I removed 26, that'd be 2 to the 0 minus 1, and the block would be empty. Here, if we removed 53, if that was the smallest one, then this would be 2 to the 1 minus 1, which is equal to 1. If I remove the smallest one from this block only here, this would be 41, right? This would be 2 to the 2 minus 1, which is equal to 3. And here we have 2 to the 3 minus 1, which is equal to 7. Now, does anybody see a pattern there? Any ideas? Specifically, do you see a pattern with the remaining elements in the blocks? Any ideas? Here, let me press escape so I can see if we get anything in the chat. So in this case, if I were to delete this, there would be no elements there and it would be 0. If I were to delete 53, there would be 1 block. If we were to delete 41, this would be 3 blocks. And let's say I had 17 there and I deleted it, this would be 7. Let me give you, oh yes. Let's do the n minus 1, very good. So let's break down this pattern even further. So 2 to the n minus 1 in 3, okay, so let's look at 1. Is that a power of 2, right? So let's break down 3. I have 1 and 2. Does everybody see that? Now we're going to do the same thing over here. So this would be 1, 2, and 3. So that's 2 to the 0 plus 2 to the 1 plus 2 to the 2. So it turns out that 2 to the n is going to be equal to the sum of n equals 0 to n minus 1 of, it's going to be 2 to the 0 plus 2 to the 1 plus 2 to the 2, right? I probably should, let me use I here so it's clearer. So I equals 0, 2 to the I. So in this case, we would have 2 to the 0 plus 2 to the 1 plus 2 to the 2. And that whole thing is going to be plus 1, right? So this becomes 1 plus 2 plus 3, and then that's going to be plus 4, and that will give us, and plus 1, that will give us 8. So the whole idea here is that when we subtract 1 from a full block, we actually get several subblocks of valid binomial values. And so that's what's going on here in the next slide. So here, 2 to the k minus 1 is equal to I equals 0 to k minus 1. And now what happens is over here, I deleted 17, but instead of having one big block that contained 8, I broke it down into 3 blocks that contained 1, 2, and 4, which sums to 7. So this property becomes very beneficial when we want to figure out how to balance. Because what I can now do is I can now say, I can now sort these elements by size. So I could take 45 and move it over here. I could take 27 and 28 and move it over there. And then I can start recombining. So log n of runtime uses plus meld. So what this means is what I'm going to do is I'm going to, I'll show you the steps here. We'd have 26, and then 45 would be over here. And then I would take the sizes of 2 and put them in order by smallest element. So this becomes 27 and 28. And this becomes 53 and 58. And then I would sort the sizes of 4 and put them there as well. So this becomes 64, 62, 23, 59. And then this becomes 64, 41, 97, and 93. And then that last part is the meld. The melding part is where we can take this and go, well, these sum up to 2, these sum up to 4, and these sum up to 8. So 8 plus 4 plus 2 becomes 14. So when I do this, we can sort the boxes by size, and then we combine the 2 to the 0 into 2 to the 1 box. Then we combine the 2 to the 1 boxes into a 2 to the 2 box, and then we combine the 2 to the 2 boxes into a 2 to the 3 box. So this binomial property allows us to be able to figure out what it is that we would want to be able to solve. So here what happens is, if I wanted to get the smallest value, I'd say, well, what's the smallest value of 26, 27, and 23? So therefore, 23 is our new minimum value. All right, does anybody have any questions before I continue? All right, so thought question. How can we represent our packets to support the operation efficiently? Well, we know that if we take away one element from the box, Aaron, come here. Come here, Aaron. Come here. No? I'm just you gotta answer the question for me? You gonna help me out here? You're so good. Right. What happens if we were to take one out and go that way? She's like, I'm just gonna go get my pheasant. Okay, didn't quite work. All right, so what's gonna happen is when we delete one, we have 3 subblocks. So if we have 2 to the 8, that's 2 to the 3, right? If we have 8, that is 2 to the 3, which means I have 3 subblocks and a smallest value, right? So what happens is I can lift that value up and I now have the subblocks, which means that if I were to pop it off, all I would need to do is I would just remove this element, and then these elements would be moved into the next level, which makes it easy to sort them, which makes it easy to then perform the melding. Does everybody see that? So therefore, this is how we sort everything. So now we have one other point. This becomes 41, and then we could have 64, 93, and 97. And that's why on the next slide, it's going to look like this. Because we have 2 to the 0, 2 to the 1, plus 1. That gives us 2 to the 2. And now it's going to give us 2 to the 2, 2 to the 1, 2 to the 0, plus 1 is going to give us 2 to the 3. So this is where we use this binomial property to be able to put these things together. So now let us formally define a binomial tree. So it took a little bit of changing the way that we think, and therefore what we can do is we can say, all right, now that I can see how binomial properties that we were discussing all the way back in calculus, I can see how we can apply this to an efficient data structure. So a binomial tree of order k is a tree structure with 2 to the k nodes. So in this case, the example I was showing you before, it's, let's say 8, right? So 8 is 2 to the 3, so k is equal to 3. So therefore, it obeys the minimum heap property consisting of a root node whose children are binomial trees of the order 0, 1, and 2. All right, does anybody have any questions about the formal definition before I continue? All right, so we can mechanically describe binomial trees as follows. Place the minimum of the 2 keys at the node root, then regroup the remaining elements, and we saw how we can sort them based on the animation from earlier. Then we recursively build the binomial trees from each group, and then we make those new trees the children of that group. Does that make sense? Okay, so why are they called binomial trees? We see that they're all 2 to the 1, and that each subtree has a small element. So the size has to be a power of 2. We have to be able to efficiently fuse them. So for example, if I take out the smallest element, I need to be able to then pop it off. And so effectively fractoring, which is what I've discussed before. And when I take that 23 off, what we're going to see is that all of the binomial subtrees are going to be sorted in a way in which the new smallest element in those binomial subtrees is immediately found. Should we see that? Okay, so first we also have to think about this idea of melding. So in melding, it used to addition to combine all the trees. So we have big O log of n time, and a cost is big O log of n plus big O log of m. And that's the size of the two trees. Then we have to do an insertion. So what I would ask you on an exam is I'd ask you to perform several insertions and then select the final binomial heap that allows us to, that gives us the final result. So you're gonna have to be able to insert, you have to be able to find the minimum, and then you'll need to be able to delete the minimum. So in deletion of the minimum, you need to show me how it is that you would be able to gain the final tree. All right, so a quick note, you probably heard me kind of slip up and say binomial Q. The reason why I said that is because they are often used interchangeably. They have a binomial Q and a binomial Q. They are technically, by the National Institute of Standards and Technology, referred to as binomial heaps. So that's why you're going to hear me refer to them as binomial heaps. However, they are often referred to as binomial queues because they're so often used in the implementation of priority queues. So as a result, if you hear binomial queue versus binomial heap, and this is going to be the same thing, you're going to hear Fibonacci heap versus Fibonacci queue. When you get to algorithms, those are going to be synonymous. So, and I've included the link to the national standard there. All right, so what I would like to do is I'd like to work with you through a couple of examples of insertion and removal from the binomial heap. So first, I just have an element of 1. So what do you think is going to happen when I insert the value 2? Any ideas? Any guesses? Yes. It'll become one's parent. Okay, so this is the crucial stuff. So let me see what it said here. Let me bring this up in the chat. So Hector says it will stay in its own cluster of size 1. All right, so let's walk through and see what exactly happened. In this case, we're going to define this as a minimum binomial heap. So what's going to happen is we're going to insert it, and then 2 is going to become the child of 1. But I see what you're thinking. You're thinking maximum. So the reason why, if we saw this in an animation, it would go 1, and then it would go 2, and then we would perform a meld operation, and then 1 would become 2's parent. So what do we think is going to happen when we insert 3? Any guesses? Three will become another child of 1. All right, so what's going to happen here is we only merge them together. So Fang Kong, it's a good guess. But what's going to happen is we perform meld only when the sum of the values becomes a power of 2. So what's going to happen is 3 is going to become its own value over here. So let me bring up the chat. 3 becomes another root. So Tiani is correct here. So this is what's actually going to happen here. Now we're going to insert 4. And we're going to insert it, and this is the reason, another reason why we want to sort them by size. So 4 is going to see an opportunity to become, it's going to be put here. We have 1 and 1 is now going to be 2. So 3 is going to become the parent 4. And so now what do we think is going to happen? Any ideas? Yes. Yeah, we're going to meld them, and I bet that's what Kennedy. So Hector is also correct. So you're both correct. We're going to meld them. And now the crucial thing is that we see which one of these two is smaller, and then that one becomes the parent. So the way this is going to work is that 1 is going to have 2 as its first child, and that's going to have 3 and 4 as its second. So now what we're able to do is we see that we have a binomial 2 to the 0 and 2 to the 1. So that's 1 plus 2, that gives us 3 and 1. So now that gives us 2 to the 2. So summing those values up plus 1 gives us the result. So that's what's going to happen here in the animation. All right, so now we're going to insert 5. What do we think is going to happen? Okay, we have a little more confidence now. What do we think is going to happen with 5? Yes. Yep, it's going to start being its own cluster. Very good. I saw your hand up in the back, so I'll get you next. What about 6? What do we think is going to happen here? Very good. So it becomes its own cluster there. Outstanding. So now what about 7? Yes. Absolutely right. So 7 is now over here. And then if we insert 8, what do we think is going to happen? Yes, Aaron, I'm going to call on you. What's that? We're going to insert 8. It's going to become its part of 7, and then we're going to combine them together. You're so good. But what's the last thing you forgot, Aaron? That's right. We have to compare 1 and 5, and then we're going to move 1 up. And so 6 and 7, and so 5 is now going to become a child of 1. Does everybody see that? So that's what's going on here. Let me walk through that step again where I'm not being very silly with my pup. So what's going on is now we put in 8 as its own cluster. So now we check to see if we have 2 clusters of size 1 that match. So we also know that 7 is less than 8. So 7 is going to become its parent. And now we have 2 clusters of 2. We can add those together, and we know 5 is going to be less than 7. So 7 and 8 will become a child of 5. Then what's going to happen is we now compare the 2, we're now going to compare 1 and 5, and we're going to say, well, 1 is less, so 5 is now going to become the next child of 1. And so again, we maintain the binomial property because what we're saying here is what we have here is we still have 2 to the 0, 2 to the 1, 2 to the 0, 2 to the 1, and this becomes 2 to the 2. And we sum those up and add 1, and now we have 2 to the 3. And then finally, we would have 9. So now I want to walk through this again, do another example. 1, 9, 8, 2, 7, 6, 5, 3, and 4. So here we're going to have 1. Then we're going to insert 9, and 9 will become its own initial value. And then we merge them together, and now 9 is going to be part of 1. When I insert 8, the animation skipped here. So I would insert 8 and then 2. And then what we're going to see is that 2 is going to be smaller than 8. So 8 is going to become the child of 2. And then we compare 1 and 2. And 1 is going to become the parent of 2. So now we insert 7. And then we're going to insert 6. So 6 is going to now become the parent of 7. Remember, we only meld when we have two that are the same size. So now we're going to do 5 and 3. So now 3 is going to become the parent of 5. We now have two values of size 2. So now 3 is going to become the parent of 6 because 3 is less than 6. And then we compare 1 and 3, and 3 is going to become the child of 1. And then finally, if we put in 4, 4 becomes its own element. All right, does everybody kind of see how that works so far? So now what I would like to do is let's talk about how it is we would extract a minimum value from a heap. So the crucial thing is we now understand that we have all of these elements, and at the top we see we have 18, 41, 53, and 26. So here's what's going to happen when we perform this deletion. What's going to happen is it's going to compare those 4 elements. So far so good. 18 is our smallest one. So that will delete, and this is where the binomial property becomes really beneficial compared to a min heap or to a doubly linked list. Here, if I get rid of that, all the subtrees, I have a subtree of 1, I have a subtree of 2, and I have a subtree of 4. Which means all I have to do is now rearrange them. So it's just going to be 26 and 45 will be over here. So we have the size of 1 and size of 1. Does everybody see that? Then I would sort these two by which one has the smallest value. So this becomes 27 and 28, and this becomes 53 and 58. So I want to ask, can someone tell me what the final 2 elements we're going to have, they're going to be next in this first step of extract the min? We have 2 final binomial tree subtrees that we need to insert here, or to rearrange. Yes. Very good. So these 2 right here, right? So then we'll put 23 and then 41 in that order. So that's the first step. So we remove that. And then what you're going to see here is that it's going to move here. 27 will move there. And 23 will move there. So now once we get to this step, now we can do the same thing that we did before. So what do you think we're going to do next? What's the first step here? Someone give it a shot. Who wants to give it a try? We got through the hard part. Now we can just do the same thing that we did before. Yes. Very good. And I bet whoever is here, Fang Kong says the same thing. So we're going to start melding together. Fang Kong says 45 will become the child of 26. So you are both absolutely right. And so now we've merged those together. So then we would move on here, like so. And then we combine these here. So 41 is now going to become the child of 23, like so. All right, so quickly, it's 11:04. So before I get into code, I'm going to go to let's go to this visualization page. And so for those of you who are, I should probably say binomial heap. There we are. I don't know why when I search for binomial Q, it didn't come up with binomial Q. All's well that ends well. All right, so what I would like you all to do is somebody throw out an integer, and I'm going to do the same thing with, I'm going to have the chat up as well. What I'd like to do is for people to just start throwing up integers, and we're going to see how the binomial heap would take care of this. So somebody just throw out a random number. 7, okay, so 7 very simply just puts it in there. Okay, so what's the, somebody else throw out another number. Okay, so we got 8 and then 15. So I heard 8 just before 15. So what do we think is going to happen here with 8? Yep. So what's going to happen is 8 is going to become its own member, and then it's going to become 7's child. So very good. So now we have 15. So what do we think 15 is going to do here? It's going to be its own cluster. Very good. And that's, I'm going to leave the chat open here so I can respond fast as well. So that's exactly right. So we're going to put 15 here, and 15 is going to become its own cluster. Okay, so another number. This is the best way to study. Just start throwing random numbers out and see what you think is going to happen. 3. Okay, so 3. What do we think is going to happen when we insert 3? Yep, it's going to become 15's parents. That's going to be the first step. And then what's going to be the next step? So it's going to be, first it's going to become its own cluster. Then it's going to add 3 and 15. And 3 is going to become the parent of 15. So now what's going to be the next step, do you think? Yeah, we're going to cluster together. And then which one's going to become the top? 3, very good. And that's exactly what's going to happen here. And that's why that happens. Someone give me another number. 12, okay. So 12 becomes its own cluster here. So another one. 35, all right. I'll start picking on somebody else, right? So 35 becomes the child of 12. All right, somebody else, give me a number. I know you all know what numbers are. 40, very good. Okay, so 40 becomes its own thing. Another one. 10, very good. All right, so what do we think is going to happen here with 10? Let's walk through the steps. Yeah, come back. Mm-hmm. Mm-hmm. Absolutely right. So what's going to happen, and let me zoom out just a tad so that way I can pause it, just so we know. So insert, the first step is it's going to become its own cluster. Then 10 is less than 40, so we will merge it like this. 10 is less than 12, so 12 is going to become a child of 10. And then 3 is less than 10, so 10 is going to become a child of 10. And so just to save a little bit of time, I'm going to say 53, which I'm just going to just say play, 57, 62, 61, 77, 8, 8's not, you're going to have double elements, and 52. Okay, so now we have it set up in a really good spot here. So what do you think is going to happen when I click this remove smallest? Let me zoom back in. When I remove smallest, first of all, what's the smallest element in this heap? What now if we insert a value smaller than 3? So actually, if I skip back, well, let me do 52, and then we'll try that one as an example a little later. Okay, so what's going to happen when I try to pop 3? Let's walk through this again. Yes. Very good. So it's going to split everything up. It's going to sort all the elements, and then we're going to start recombining. Right, so 3 is there, and it tends to work fast, but we see that's what's going to happen. So the question that Feng Kong is asking is, if I go back here, and I'm going to take one other step back. So what Feng Kong's asking is, what happens when we insert a value less than 3? So let's say I put in 2, right? So when I remove smallest, in this case, it's by itself. So if I put that in there, we sort everything out. If I were to insert 3 and then remove again, we're going to see that 3 is going to be removed and 15 is going to become its own cluster, right? If I were to skip remove smallest now, what we're going to see is that 7 is going to be removed. 8 is going to be a cluster of 1. And then 8 and 77 is going to become a cluster of 2. And we're going to see that 15 and 8 are merged like so. Does everybody see that? So that's why we can take advantage of this binomial property. So real quickly, since we have 4 minutes left, what I would like to show you is just, first I have this binomial node where I have a left child and its next sibling. Then I have my constructor where I set both the left child and next sibling to null. So constructor, copy constructor, and assignment operator. Constructor operator. And then what I have here is combined trees. So now we have a merge operation. And what's going on in this merge operation is I have 2 binomial nodes. And I say if T2 data is less than T1 data, then I just call combined trees and reverse it. Otherwise, I say T2 sibling is equal to T1 left child, and T1 left child is equal to T2. So whatever was there before, it now gets moved. And so that's what's going on internally inside the binary node, the binomial node. In the binomial heap, I have a method, find min index. And so while I'm going through the top element, I get the index. So I'm just iterating through the number of trees in this particular row, right? And then return the index of that. And then I have combined trees, which I call the combined trees method there for binomial node. And then clone. If I want to clone the subtree, this allows me to take a subtree and put it into the upper tree. So I have this binomial node, and I'm able to create a copy of it. A constructor, destructor, copy constructor, assignment operator, find min, insert. So this is what I like to show you. So I create one item, and then I call this merge method I'm going to show you. So delete min is just getting the delete minimum and then removing from it. Now, let me find merge. Okay, so merge is what a good place to spend the last 2 minutes of lecture. So if we're just if we say this is equal to the right-hand side, then we're returning, we don't want to merge 2 elements to each other, an element to itself, excuse me. So then what I do is I say we add the current sizes of the 2 binomial heaps. So we're merging 2 binomial heaps here. So if one has a size of 4 and one has a size of 2, we're now it's going to be size of 6, excuse me. If current size is greater than the capacity, then what we're going to do is we are going to get the size of the old tree that we're entering. And then what we're going to do, so a lot of this is just taking care of the sizes. And the reason why this is important, and let me show you a slide here. Rule of 3. Okay, so merge cases. So we have 3 different merge cases. So we have a little flow chart that I'm going to show you here. If temp1 is equal to null, then I'm going to say which case is equal to 1. Otherwise, which case is equal to 0. And then I'm going to check if temp2 is equal to null. Then I'm going to say which case plus equals 0, no, plus equals 2. And then here, if it's yes, and if it's no for current, then I'm going to say which case plus equals 3. And what's going to happen here is I have several cases Where are the cases here? Oh yeah, so here's which case, and switch which case, and then in all of the cases that we've covered, there are actually there are 8 total cases, excuse me. Of case 0, there's no tree. So if we say, yes, there's no current, yes, there's no left, and yes, there's no right, there's no binomial heap at all. If we have 1, then only temp 1 exists. If we have 2, then only the right-hand side node exists, and we move the right-hand side up. Case 3, that means we get a 1 plus 2. That means that this and the right-hand side means that there's no carry node. So the carry is going to be the result of when we combine the temp trees. And then we set this particular node at I equal to the right-hand side equal to null. If we have 2 and 2, that means only the carry node exists. Or is it 1 and 3, excuse me. Only the carry node exists. So therefore, we just set I equal to the carry node. And we set that previous carry equal to null. All right, so it's 11:16. So I'm going to very, very quickly go through case 5, case 6, and case 7. We have this carry, only this and carry, and then case 7 is all 3. So in the case of all 3, we set the trees I equal to the carry, which is coming in. Then we combine the right-hand side and the left for temp 1 and temp 2, and then we set the previous right-hand side equal to null. Right, does anybody have any questions about that? All right, on that note, have a good weekend. Make sure you reach out to your project manager if they haven't reached out to you, coordinate that, and make sure that you convey your progress. And if you read that, you'll have a really good idea of what the expectation of the meeting should be.